Okay, so let's see what we have here. We'll have two sets of two batteries in series. So what's going to happen with these is if you take, let's see, they're each 1.5 volts. Every time you go up one of these batteries, you increase the potential by 1.5 volts. So that's the electromagnetic force that's there. So it's going to be twice whatever the rating is, the delta V, for one of these batteries. So it's going to be twice delta V going up. Doesn't matter if the electron goes up on the bottom side or on the top side, it's still going to go up the same amount. It has to go up the same amount, in fact, because this is all connected by an ideal wire. So that's going to be 2 times 1.5 volts, or 3 volts. So the amount of potential is going to be 3 volts. So if this is 0, this is connected to a ground here, then at this point up here it's 3 volts. It's gone up 1.5 and then another 1.5, 3 volts. Okay, so that's part 1. Go from 0 volts to 3 volts. Very good. But now we want to figure out if, when this is connected to a device, right, DUT, device under test, then how long is that actually going to last, right? So I called this the lifetime. Q equals 20 amps times an hour, amp hours. But you'll remember that an ampere is equal to a coulomb per second. Multiply that by an hour. Hours are actually denominated in seconds. So you multiply this by 3600. That's going to give us the total number of coulombs, the total amount of charge on there. So I'm going to say the total amount of charge that can be applied, the sort of lifetime, is the current it'll put out times the time it'll put out. Okay, so that's going to be T equals Q over I. Just said Q was 20 amp hours. And so this was 100 milliamps when connected to this DUT. So the current is 100 milliamps, and that's 0.1 amps. And so that's going to be equal to, well, it's actually, I messed up. You get 20 for this one and 20 for that one. So it's twice that, right? You get 20 for this one, 20 for that one. So each parallel one gives you some additional time, right? It gives you additional charge that you can apply through your current. And so that's going to be 400 hours there, which is about 16 and 2/3 days. So 16 and 2/3 days. So these were kind of independent. This was saying basically what happens when you put the batteries in series. Put batteries in series, you go up a higher potential, so you have a higher energy. You have a higher potential, so that's a higher energy per electron, right? So 1 volt is basically um, 1 volt is, well, remember that the energy, this is bad, this changed font when I switched devices. Your energy is basically your charge times your voltage. So an electron that goes up here, each battery takes it up a step, increases its potential a little bit. And each one of these guys, each one of these parallel banks, increases the lifetime by the amount of charge it has, which is 20. Each one of these has 20. So doesn't matter that these are in series because these guys are both providing the energy, right? These guys are both providing the energy, then it takes just as long for them to lose that energy. So that's more or less what happened in this particular setup. Those are the two things that we do for the batteries. We know we have the amount of power or the amount of voltage. It puts in the amount of electromotive force, which is related to the power, but it's not the same thing. And then we have the duration that force can be applied, electromotive force can be applied.